the condition for exact differential. This we have already done when we talked about point functions and property. So if you remember, for a particular variable to be a property, it should be an exact differential. And we have seen that initially, and we have said dz equal to partial z partial x at constant y into dx plus partial z partial y at constant x into dy, where this partial z partial x can be replaced with m and partial z partial y can be replaced with n, and we can say dz equal to mdx plus ndy. If the equation dz equal to mdx plus ndy has a solution, dz is an exact differential. This is what we have seen. Okay, so keep that in mind. So keep that in mind. And what we saw was, so for this dz equal to mdx plus ndy, the condition for exact differential was partial m partial y at constant x is equal to partial n partial x at constant y. So this is the condition for exact differential. Okay, we have seen this. So just keep that in mind. We will be requiring that later on. Okay, so let's start with the first law of thermodynamics. So in the first law of thermodynamics, what we did was, we said, the first law of thermodynamics, we said dq equal to du plus dw. Okay, and if you remember, we can replace this dq with tds. So tds is du plus pdv. So for a closed system, we can write it like this: W equal to integral pdv for a closed system and a quasi-static process. So we can say du equal to tds minus pdv. Okay, and let me call this as equation number 1. And if you look at this equation carefully, you can observe something. And let me come to that later on. Okay, so this is equation number 1. And we can define, or we have defined already, that enthalpy is U plus PV, right? We have defined enthalpy as U plus PV, that we have done already. So if I differentiate it on both sides, what I'll have is dH is equal to du plus d of PV. And if I expand it, I can write this as du plus PdV plus VdP. And equation 1 tells me that this du plus PdV, this du plus PdV is nothing but TdS. So I can replace this du plus PdV with TdS. So TdS plus VdP. And so this is dH. And you, once again, you can observe, if you observe this equation, you will find something. So let me call this as equation number 2. Okay. Now let me take equation number 1 So from 1, du equal to TDS minus PdV. So this equation, if I write this as du minus TDS equal to minus PdV. Okay, and now what I want to show you is, so just like we wrote d of PV as PdV plus VdP, we can write d of TS as TDS plus SDT. And so I can write TDS is equal to d of TS minus SDT. Okay, and I can substitute for this TDS in this particular equation. So I want to substitute this equation and replace this TDS term. So if I do that, what I'll have is du minus d of TS plus SDT equal to minus PdV. And because I have the differential sign here in the first two terms, I can couple them and write this as u minus TS, and I can take the other to the right hand side, minus PdV and minus SDT. And I can call this u minus TS as F, which is called as Helmholtz function. This F is called as Helm, H-E-L-M, another H-O-L-T-Z, Helmholtz function. So we can write this as df equal to minus PdV minus SDT. So this is equation number 3. From equation number 2, just like I have done from equation number 1, I can also do for equation number 2. So from 2, what I can do is, so equation number 2 is dH equal to TDS plus VDP. So instead I will write this as dH minus TDS is equal to VDP. Okay, and just like I replace this TDS with d of TS minus STT, I'll replace this TDS also. So I'll replace this TDS with dH minus of d of TS plus SDT equal to VDP. And just like I've done before, because I have the differential in both these, I can couple them and write this as d of H minus TS which is equal to VDP minus SDT. And this H minus TS is replaced with G, and this is called as Gibbs function. GI BBS, Gibbs function. Okay, and we can write this as dg equal to vdp minus sdt. So this is equation number 4. And if you look at all the 4 equations, from equation number 1 and 2, it's very clear that change in internal energy is a property, temperature is a property, change in internal energy is a property, pressure is a property, volume is a property. All these are properties. Enthalpy is a property, temperature is a property, entropy is a property, volume is a property, pressure is a property. If you look at it, we have not seen Helmholtz function and Gibbs function before. But if you look at the right-hand side, all are properties, so Helmholtz function should also be a property. Here, the right-hand side, all are properties, so Gibbs function should also be a property. So equations 1 to 4, everyone is a property. So you can apply the relation which we have seen before, the condition for exact differential dz equal to mdx plus ndy. If you look at it, all the 4 equations are similar to dz equal to mdx plus ndy. So you can apply the condition for the exact differential for all these 4 equations, and you will get a set of results. Okay, so if you apply this, so partial m partial x at constant y. Okay, so I'll just complete this so that one part will be over and we will close the session because it's already time. So the first equation is du equal to TdS minus PdV. So this is similar to the form dz equal to mdx plus ndy. So n you can take it as minus p. So the condition is partial m partial y at constant x. This is equal to partial n partial x at constant y. Okay, so if I look at the previous equation and write, I can write this as, so m is likened to t partial v at constant s. This is equal to, so there is a minus which can be taken outside, partial p partial s at constant v. Okay, so let us call this as one particular equation. And the second equation was dH equal to TdS plus VdP. And if I apply the same conditions as before, so partial t partial p at constant s is equal to partial V, partial S at constant V. This is number 2. The third equation was dF equal to minus PdV minus SDT. So minus partial P by partial T at constant V is equal to minus of partial S by partial V at constant C. Because you have minus on both sides, you can just cancel it so that it becomes positive on both sides. So this is equation number 3. And equation number 4 was dG. This is equal to VdP minus SDT. So once again, this will be partial V, partial T at constant P, sorry, yeah, correct, partial T at constant V. So this would be minus of partial S, partial P at constant. And this is equation number 4. And these 4 relations are called as Maxwell's relations. These 4 relations are called as Maxwell's relations. The advantage with Maxwell's relation is if you observe all the 4 relations, you will find the temperature, volume, pressure. These 3 are measurable. Entropy is not measurable. You can measure temperature with a device. You can measure pressure with a device. You can measure volume, maybe with a ruler or something. Okay, you have so many measuring devices. But entropy we can't measure directly. So, but you are able to get the value of entropy with the help of pressure, volume, and temperature. Even here, you can find temperature, volume, and temperature, pressure, and volume in terms of entropy. Here also, temperature, pressure, and volume in terms of entropy. Okay, so that gives us Maxwell's relations. Okay, so that is the advantage of having Maxwell's relations. So you are able to measure, or you are able to estimate entropy in terms of measurable properties, pressure, volume, and temperature.